Here is a combined summary of the 2 pages. The study investigates the anisotropic behavior of swave and wave states of heavy quarkonia at finite magnetic fields using an extended magnetized effective fugacity quasiparticle model, EQPM. The real and imaginary parts of the potential are modified through the dielectric function by including the anisotropic parameter Xi. The binding energy of the 1s, 2s, and 1p quarkonium states, including anisotropy effects, are studied for both oblate and isotropic cases. The results show that the binding energy of QQ states becomes stronger in the presence of anisotropy, while the magnetic field reduces the binding energy. The thermal width of the charmonium and bottomonium 1s states are studied at a constant magnetic field of Eb equals 0.3 GeV² for isotropic and prolate cases. The effect of the magnetic field on the mass spectra of the 1p state for the oblate case is also examined. The dissociation temperature for the 1s, 2s, and 1p charmonium and bottomonium states are determined to be higher for the oblate case with respect to the isotropic case. The EQPM is used to study the anisotropic behavior of heavy quarkonia in the presence of a strong magnetic field. The distribution function for quasigluons and quasi-quarks, quasiparticles are given by equations 1, 2, and 3, which include the effective fugacity parameter Zg for gluons and Zq for quarks, encoding all the interacting effects taking place in the medium. The Debye screening mass is defined as the ability of the plasma to shield out the electric potential applied to it and is calculated using the gluon self-energy, modified by the magnetic field. The study highlights the importance of including momentum anisotropy in the study of quarkonium properties in the magnetic field regime, as the QGP produced in non-central collisions does not possess isotropy. The results of this study have implications for the understanding of the quark-gluon plasma, QGP, and its properties in the presence of strong magnetic fields, which is relevant to heavy-ion collisions and cosmological aspects. In the presence of a magnetic field, the Debye screening mass is derived using both perturbative QCD and kinetic theory approaches, yielding similar results. The Debye mass for non-interacting quarks and gluons is given by equation 9, while the two-loop coupling constant alpha depends on temperature and is expressed in equation 10. The quark-antiquark potential in an anisotropic medium is studied using a modified Cornell potential, which includes both Coulombic and string parts. The potential is modified using a Fourier transformation to account for the anisotropy. The anisotropic distribution function is introduced at the particle distribution level, and the parameter Xi represents the anisotropy of the medium. To maintain the Debye mass intact from the effects of anisotropy, a normalization constant Xi is introduced, which is given by equation 12. The Debye mass remains the same for both isotropic and anisotropic cases. The normalization constant Xi can be simplified for small anisotropic effects, as shown in equations 13 to 15. The potential of the dissipative anisotropic medium is modified in the Fourier transform by dividing it with the medium dielectric permittivity, as shown in equation 16. The in-medium, corrected potential is obtained by taking the inverse Fourier transform, given by equation 17. The dielectric permittivity is calculated using 2 methods: gluon self-energy in finite temperature QCD and semi-classical transport theory. The dielectric tensor in the Fourier space is written as equation 20, which provides the relation between the dielectric permittivity and the gluon propagators. The real and imaginary parts of the dielectric tensor are given by equations 21 and 22, respectively. The variation of the real potential with distance r for isotropic and oblate cases is shown in Figure 1, demonstrating the effects of anisotropy on the quark-antiquark potential. Overall, this study investigates the Debye mass and quark-antiquark potential in an anisotropic medium, incorporating the effects of magnetic fields and anisotropy. The results provide insight into the properties of heavy quarkonia in high-temperature QCD, relevant for understanding heavy-ion collisions. The research discusses the properties of heavy quarkonia, focusing on the binding energy and dissociation temperatures in the presence of anisotropy and strong magnetic fields. The binding energy of the 1p states of charmonium and bottomonium is calculated, considering the correction term for the kinetic energy. The dissociation temperature is determined by the conditions ebb is less than or equal to T and gamma T is greater than or equal to 2 exabytes, where gamma T is the thermal width. The thermal width of the one state is also calculated using the Coulombic wave function. The study highlights the importance of considering anisotropy in magnetic fields in understanding the behavior of heavy quarkonia under extreme conditions. The paper explores the variation of binding energy for different quarkonia states under varying magnetic fields and temperatures. It focuses on the isotropic and oblate cases, examining how these conditions affect the quarkonia's stability. In Figure 2, the binding energy of the J psi is presented as a function of temperature for both isotropic and oblate scenarios at different magnetic field strengths. The results indicate that the binding energy decreases with increasing temperature in both cases, although the oblate case exhibits a more pronounced decrease. This suggests that the stability of the J psi is influenced by the magnetic field and temperature, with the oblate case being more sensitive to these factors. Figure 3 illustrates the binding energy of the upsilon as a function of temperature for isotropic and oblate scenarios, also at different magnetic field strengths. Similar to the J psi, the binding energy decreases with increasing temperature in both cases. However, the oblate case shows a more significant reduction in binding energy compared to the isotropic case, indicating that the upsilon is also affected by the magnetic field and temperature, with the oblate case being more sensitive. Figures 4 and 5 depict the binding energy of the psi and upsilon as functions of temperature for isotropic and oblate scenarios at different magnetic field strengths. The trends observed in these figures are similar to those in Figures 2 and 3, with the binding energy decreasing with increasing temperature in both isotropic and oblate cases. Again, the oblate case exhibits a more pronounced decrease in binding energy compared to the isotropic case, suggesting that the stability of the psi and upsilon is influenced by the magnetic field and temperature, with the oblate case being more sensitive. These findings highlight the importance of considering the effects of magnetic fields and temperature on quarkonia stability, particularly in the context of heavy-ion collision experiments. The results provide insights into the potential dissociation mechanisms of quarkonia, which can be crucial for understanding the properties of the quark-gluon plasma. The paper's conclusions underscore the need for further research to fully understand the interplay between magnetic fields, temperature, and quarkonia stability. Here is the combined summary. Figure 6 illustrates the variation of binding energy of the chi-C with temperature for both isotropic and oblate cases, across different values of the magnetic field. The left panel presents the isotropic case, where the binding energy decreases with increasing temperature, exhibiting a monotonic behavior. In contrast, the right panel displays the oblate case, where the binding energy initially decreases with temperature, but then undergoes a slight increase at higher temperatures. This deviation is attributed to the anisotropic nature of the oblate case, which introduces additional complexity in the binding energy's temperature dependence. Moving to Figure 7, we observe the variation of binding energy of the chi-B with temperature, again for both isotropic and oblate cases, under varying magnetic field strengths. The left panel, corresponding to the isotropic case, reveals a similar monotonic decrease in binding energy with temperature, akin to the chi-C case. In the right panel, the oblate case exhibits a more pronounced deviation from the isotropic behavior, with the binding energy displaying a non-monotonic trend. The interplay between temperature and magnetic field strength is evident, with the binding energy responding differently to these variables in the isotropic and oblate scenarios. These figures collectively highlight the significance of anisotropy in modifying the binding energy's response to temperature and magnetic field variations. The chi-C and chi-B states demonstrate distinct behaviors, underscoring the importance of considering both isotropic and oblate cases when modeling these systems. The presented results provide valuable insights into the intricate relationships between temperature, magnetic field, and binding energy in these systems, paving the way for further investigations into the underlying physical mechanisms. The research paper investigates the properties of heavy quarkonia in an isotropic hot QCD medium at finite magnetic fields using the extended quasiparticle model. The study focuses on the mass spectra and dissociation temperatures of various quarkonium states, including J, psi, upsilon, chi-C, and chi-B. The real potential of the Cornell potential is modified to incorporate the effects of anisotropy and magnetic field. The mass spectra of the quarkonium states are calculated using the relation m equals 2mq plus Eb, where mq is the mass of the heavy quark and Eb is the binding energy. The binding energy is obtained using the variational treatment method. The results show that the binding energy of all quarkonium states decreases with temperature and magnetic field for both isotropic and oblate cases. However, the binding energy has higher values for the oblate case, Xi equals 0.3, compared to the isotropic case, Xi equals 0. The dissociation temperatures, which are calculated using the binding energy, also decrease with magnetic field for both cases. The study finds that the anisotropy has a significant impact on the properties of quarkonium states. The binding energy and dissociation temperatures are higher for the oblate case compared to the isotropic case. The thermal width of charmonium and bottomonium states increases with temperature and magnetic field, with the upsilon state having a smaller thermal width than the J-psi state. The paper presents the results in various tables and figures, including the upper bound of dissociation temperatures for isotropic and oblate cases, the variation of binding energy with temperature, and the mass spectra of chi-C and chi-B states. The study concludes that the extended quasiparticle model is a useful tool for investigating the properties of heavy quarkonia in an isotropic hot QCD medium at finite magnetic fields. The future scope of this work includes calculating the survival probability or nuclear modification factor of different quarkonium states with respect to transverse momentum, centrality, and rapidity, which is essential for understanding the properties of the medium produced during heavy ion collisions. In the context of heavy ion collisions, the study of quarkonia in strong magnetic fields has garnered significant attention due to its potential implications for understanding the quark-gluon plasma, QGP. The QGP is a state of matter that exists at extremely high temperatures and densities, such as those found in the early universe or during high-energy particle collisions. In this state, quarks and gluons are deconfined, leading to a plasma-like behavior. The formation of the QGP in relativistic heavy-ion collisions was first proposed by Landau and Lifshitz in 1984. This idea was further developed by Matsui and Satz in 1986. Who suggested that the QGP could be identified through the suppression of quarkonia, such as J, psi and upsilon. This suppression occurs when the binding energy of the quark-antiquark pair is weaker than the Debye screening mass, causing the quarkonia to dissociate. Several studies have been conducted on the effects of magnetic fields on quarkonia, including the modification of their mass spectra and the potential for enhanced production. For instance, Cho et al. Used QCD sum rules to study the mixing between eta C and J, psi in strong magnetic fields, while Guo et al. Examined the effects of magnetic fields on charmonium production in high-energy nuclear collisions. In addition to quarkonia, the behavior of other particles in the QGP has also been investigated. For example, Romachky and Strickland studied the collective modes of an anisotropic QGP, while Martinez and Strickland explored dileptin production from an anisotropic plasma. Furthermore, Baer and Matar-Tani investigated jet quenching and broadening in unstable non-abelian plasmas. The presence of magnetic fields in heavy ion collisions has been addressed by several authors. For instance, Voronyuk et al. Estimated the magnetic field strength in such collisions, while Dumitru et al. Examined the heavy quark potential in an anisotropic plasma. Moreover, Bernier et al. Analyzed quarkonium dissociation in the presence of a small momentum space anisotropy. The study of quarkonia in strong magnetic fields is crucial for understanding the properties of the QGP and its potential implications for our understanding of the early universe and high-energy particle physics. This research area continues to evolve, with ongoing investigations into the effects of magnetic fields on quarkonia and other particles in the QGP. Here is a combined summary of pages 15 and 16 of the research paper. The authors have conducted an extensive review of various studies related to quark-gluon plasma, quasiparticle models, and quarkonium dissociation in hot QCD medium. The references cited in the paper cover a wide range of topics, including lattice QCD, quark-gluon plasma, quasiparticle models, transport properties, and quarkonium dissociation. The authors have reviewed various quasi-particle models, including those proposed by Chandra and Ravishankar, Peshier et al., and Manohar, which aim to describe the quark-gluon plasma in terms of quasi-particles with non-trivial dispersion relations. These models have been used to study the equation of state, transport properties, and quarkonium dissociation in hot QCD medium. The paper also reviews studies on quarkonium dissociation in hot QCD medium, including those using quasi-particle models, complex potential models, and lattice QCD simulations. The authors have cited references on the dissociation of heavy quarkonia in anisotropic hot QCD medium, as well as the effects of magnetic fields on quarkonium dissociation. Furthermore, the authors have reviewed various approaches to studying quark-gluon plasma, including thermal field theory, hard thermal loops, and classical transport theory. The paper also cites references on the relativistic wave equations in momentum space and the relativistic two-body Coulomb system. The authors have also reviewed recent studies on quarkonium production and suppression in nuclear collisions, including those using effective fugacity quasi-particle models and lattice QCD simulations. The paper concludes by citing references on the review of particle physics, including the Particle Data Group (PDG) review. Overall, the paper provides a comprehensive review of various studies related to quark-gluon plasma, quasi-particle models, and quarkonium dissociation in hot QCD medium, highlighting the importance of these topics in understanding the properties of matter at high temperatures and densities.